Chapter 4, Axial Load Part B. Just consider we do have a cylindrical bar which is hanging from a horizontal fixed support at the top here. We want to calculate the axial increment in bar length at the end B due to weight of the bar. So we do have a cylindrical rod AB with a length of L and weight of W, which is hanging from a horizontal fixed support at the top. We want to know what is the deformation at the increment of the length at B due to the weight of the rod itself. Before solving this problem, let's go by a, a horizontal scenario, which a rod AB, cylindrical rod AB with the specification of EA, happen to a tensile force of F equal to W over 2. If you want to calculate the delta at B from what we learned in part A, that delta B is nothing but W uh, over 2 times L over EA, which gives us a WL over 2 EA. And let's now rotate our problem to a by a 90 degrees to reach the vertical case, but with the same force of W, concentrated force of W over 2 at the end B. Mhm. We simply know WB is W delta B is WL over 2 EA for a horizontal case. Let's due to similarity just assume the vertical case should be similar to the horizontal one or a kind of similarity. Find a kind of similarity between them. So let's back to our problem, horizontal vertical case. In if you just remember from part A, delta goes with the two main scenarios of this one discrete part and continuous shapes. So, and I just put the link of axial load part A just in case if you want to review that material. So in our problem, delta can be discrete and continuous, but that discreteness and continuous condition could be due to the shape of the structure. But at the same time, it can go a bit farther with a closer look to consider we can do have that discrete and continuous condition also due to the loading itself. So we can have four condition: one, discrete shape, discrete loading; discrete shape, continuous loading; continuous shape, discrete loading; continuous shape, continuous loading. So in our case problem, what we need to handle is a discrete shape. Definitely there is only one cylinder with the uniform at the entire cross section, but due to axial increment, due to its weight, it's a continuous loading. So we do have this scenario. And if you have any continuous condition in any case, you need to go by integration. That's integration from 0 to L. So now let's attempt our problem. So, If we just consider our solution, delta is nothing but integration from 0 to L Wx dx over Ea. And we also know W is Wx is gamma times volume, and that's gamma times cross-sectional area, which if we define an element over here with the length of x and cross-sectional area of A, the volume of this part its volume, it's A times x, and the weight for the whole structure is gamma times A times the length of the whole uh, uh, bar, vertical bar. And if we just take the constant out of integration, gamma A comes out, EA in denominator comes out of integration, then we integrate 0 to L x dx. If we cancel out the areas, delta is gamma over E x squared over 2 from 0 to L. And that's gamma L squared over 2E. From 1, we can just replace W by weight over AL, which goes here. Gamma L squared over 2E. We just replace gamma with W over AL. And if we simplify delta, it just shows delta is WL over 2EA, which is exactly the same case in horizontal condition. And that's an interesting fact that a as if we are replacing distributed load of W with the concentrated load W over 2 at the end B. And that's a very interesting fact which says with this uh, simulation we can uh, ignore all the integration process and just replace the distributed load by a concentrate of half of that weight at the end of B. Let's see how that works in a problem solving. So consider we have a shape of two cylindrical bar with different uh, weight, different material, and different length hanging from a fixed support at the top here. Uh-huh. And again, we want to know what is the delta at C. Mhm. So it just goes delta C is delta C with respect to B for the first part and plus delta B with respect to A for the second part. Mhm. Let's approach the problem and forget about the integration by just the simplified method which I just showed you. In that case, delta C is the summation of the delta of both parts, and for delta CB, it just assume we are replacing the concentrated load of W, distributed load of W with a concentrated load of a W over 2 at the end C times the length of this structure over EA, which gives us WL over 4 EA. For the second part, delta BA is we can replace the distributed load of 3W with the concentrated load of half of that at the end B. So that's 3W over 2 plus the extra hanging load. So this part is like attachment to the top part, and that's a load of W because this is the separated part attached to the top one. So W plus 3W over 2 times the length of AB over 2EA, which is the specification of part AB. And that goes by 5 over 4WL over 4EA. And delta C is nothing but the summation of those two. And if you do the math, it gives you delta C, it's uh, 3WL over 2EA. And that's very interesting because it makes the problem far easier, ignoring the integration of part A, B, and BC.